Hello, thanks for clicking. Welcome to another Argulus 2 production. Today we're going to be talking about Lagrange's error bound. Okay, this is used to approximate a function, a function's value using its Taylor polynomial. All right, and predict what the error would be or a maximum for that error. All right, so let's take a look at how this works. So far, we know that if a series converges and it alternates, we can use the alternating series error bound to find the largest error in the actual sum, right? So the largest error in the actual sum, we know, is the term after the one that we were supposed to use, okay, to evaluate. All right, so we evaluate the thing using the first 5 terms, then the sixth value or the sixth term would be the maximum error that you could have. Okay, so again, that's how it works for an alternating series, right? But not all Taylor series alternate. So the question is, how would we do this if we're going to use a Taylor polynomial to approximate the value? So basically, the idea behind what we're going to try to accomplish is this. Let's say I had a function f of x is equal to e to the x. And I wanted to use, let's say, or find the third, now we'll do second degree Taylor or Maclaurin polynomial. So that's about x equals 0, right? So see, the center is 0. The center is 0. And what I want to do is I want to approximate f of 0.1. I don't know, whatever it is. All right, so could we find the second degree Maclaurin polynomial for e to the x? Well, sure we could. To do that, the second degree Maclaurin polynomial would be f of 0 plus f prime of 0 x minus 0, right? Plus f double prime of 0 over 2 factorial x minus 0 squared, or x squared. And then we just got to find f of 0, f prime of 0, and f double prime of 0, which are easy, right? F of 0 is e to the 0, it's 1. F prime of x is e to the x again, so f prime of 0 is also 1. And then f double prime of x is e to the x again, and f double prime of 0 is also 1. So the second degree Maclaurin polynomial with respect to x is 1 plus 1 times x plus 1 over 2 factorial x squared. Now, if I wanted to use the second degree Maclaurin polynomial to approximate f of 0.1, I could do that, right? I literally just take 0.1 and I substitute it in, and it'll give me a value, and that value would represent the approximation. Okay? So how does that help me? So this is the approximate value, right, of f of 0.1. But it's not the true value of f of 0.1. To find the true value of f of 0.1, I literally have to take 0.1, substitute it in, and that would give me the true value for this function, right? Now, this Maclaurin polynomial is not the right answer, all right? It's wrong. It's off, right? Well, by how much is it off? I don't know, but I could figure out how much it would be off if I take the true value and subtract away the Maclaurin polynomial's value, let's say an absolute value. So this is the true value. And then I'm subtracting away the approximate value. Well, that would give me the error, right? Or, as they like to call it, the remainder. Okay? This is the error in the true value. All right, how far off are you from the correct answer? Okay? Now, the question is, how do we find this error? And that's what Lagrange's error bound is all about. How can we figure out how far off we are? Because the issue is, you're not going to know what the true value is. Because if you knew what the true value was, you never would have tried to approximate it with the Maclaurin polynomial. You literally just would have found the true value. Why bother approximating with the Maclaurin polynomial then? I could just take 0.1, find e to the 0.1, type it in a calculator, and it gives you your answer. But back a long time ago, didn't have calculators to work with. So this was not as easy as a calculation as it might look, or it looks today. All right? So what we want to do is figure out how you find that remainder. And to do that, we have two people to credit. Taylor polynomial guy, and Lagrange. So let's talk about what they both said. So let's talk about the Lagrange's error bound and Taylor's theorem. Taylor's theorem says, let f be a function with n plus 1 derivatives on an interval containing c and x. C is the center, and x is the value you want to evaluate at. Then there exists a value z between x and c such that f of x is equal to, so this is the true value. The true value is equal to the Taylor approximate value plus the remainder. Right? The error, how far off you are. So if I take the approximate value and add the error, I would get the true value. Well, sure, of course you would. Now, r of n, or r sub n, is equal to the n plus first derivative evaluated at z over n plus 1 factorial x minus c to the n plus 1. So now, this is saying something. It's saying something important, but it may not be easy necessarily to interpret. Go back to that M2, or that second degree Maclaurin polynomial that we found a minute ago. That was it, right? Okay. What Taylor's saying is, if you want to find the actual error, the true error in this calculation that you did when you plugged in 0.1, you can find it by going to the next term in the Maclaurin polynomial that you don't use, very similar to the alternating series error bound. So you'd go to the third degree term, okay? You're going to take f evaluated at the third derivative at z. So what is this z? Z is a value between x and c. So z is somewhere between x and c, or depending on how your inequality works, c and x, whichever one's smaller goes first, right? Okay. The center, so z is a number between the center, where the Maclaurin polynomial is centered, in this case 0, and x, the number you want to evaluate at. So in my case, up here, we'd be evaluating between 0 and 0.1. Z is somewhere between these two, or it could be either one of the endpoints. All right? And if I evaluate the third derivative at that value, somewhere between 0 and 0.1, and divide it by 3 factorial times x minus c, so 0.1 minus 0 cubed. Basically, I'd be finding this term in the Maclaurin polynomial. All right, but I'd be evaluating the third derivative at z, some number between 0 and 0.1. If I were to do that and find the right number for z, then I would get the correct error. I'd get the exact error, okay, that I would need to add to the approximation to get the true value. Well, that's all well and good, but we're talking about exact error again. Why are we going to find the exact error? How are we going to find the exact error if we don't know what the true value is? Okay, I don't know. So how can I find the exact error? So Lagrange came in and he said, look, I don't know what the exact error is going to be, but what I'm going to do is I'm going to take your idea, Taylor, that you have up here, go to the next term in the polynomial, use that, and I'm going to try to make this numerator as large as possible. So I'm going to take a number, z, somewhere between the value I want to evaluate at, in the case on the slide before, and the center. and I want to substitute it in to the third derivative, I'll take the absolute value of it, and I want the maximum value of it. So whatever number, 0, 0.1, or anything in between, that will give me the largest value for the third derivative of f, evaluated at z, third derivative because that's the one that's missing, okay? That's the number I'm going to use here. So basically what Lagrange says is he's trying to put a cap on the error. He's trying to make the error as big as possible to say that the true value has to fall somewhere between the approximation that I got and the largest error that I could get. Okay? So he's not telling you what the exact answer is. He's just telling you that the true value is somewhere between the approximate value from the polynomial and some error that you're going to calculate to be as big as possible. All right? That's how Lagrange's error bound works. Now, it sounds very, very, very complicated, but actually it's not as difficult as you might think to use in process or in practicality. All right, so let's take a look. So the function f has derivatives of all order for all real numbers x, and then you're given some values of f of 1, f prime of 1, f double prime 1, f triple prime 1. They want you to write the third degree Taylor polynomial for f about x equals 1. 1 is the center, and use it to approximate f of 1.5. Okay, so to do that, the third degree Taylor polynomial here would be, let's write it out, f of 1 plus f prime of 1, x minus 1, plus f double prime of 1 over 2 factorial, x minus 1 squared, plus f triple prime of 1 over 3 factorial, x minus 1 cubed. All right, so now let's write the third degree Taylor polynomial. So t sub 3 would be, let's start substituting numbers in. We got negative 3 plus 5 x minus 1 plus 3 over 2 factorial, x minus 1 squared, or plus, well, it should be minus. Let's make this a minus here. Minus 6 over 3 factorial, x minus 1 cubed. Okay, you could simplify that a little bit, right? 6 over 3 factorial is going to be 1, right? And now there's my third degree Taylor polynomial. I'm going to use it to approximate f of 1.5. So I'm going to substitute 1.5 in here. That's negative 3 plus 5, 1.5 minus 1, plus 3 over 2 factorial, 1.5 minus 1 squared, minus, that's really a 1 there, 1.5 minus 1 cubed. So that's going to be 3 plus 5 times a half plus 3 over 2 factorial. 1/2 squared is a quarter minus 1/8, right? Yeah, so that's going to be negative 3 plus 5 over 2 plus 3 over 8 minus 1 over 8. So 5 over 2 is really 20 over 8. And so that's going to be negative 24 over 8 plus 20 over 8 plus 3 over 8 minus 1 over 8. So that's, let's see, that's 2, 22, negative 1/4. So the third degree Taylor polynomial approximates the value at 1.5 at negative 1/4. Okay, now the fourth derivative of f satisfies this inequality. The absolute value of the fourth derivative at x is less than or equal to 3 for all in the closed interval 1 to 1.5. Use the Lagrange error bound to show that f of 1.5 minus p sub 3 of 1.5 is less than or equal to 0.008 or 8 thousandths. Okay, so now what I'm showing is f of 1.5, that's the true value. This is the Taylor approximation, right, that I got previously. And that's going to be less than or equal to 0.008. Okay, so to do that, I'm going to go to the next derivative. So the first unused term here in this Taylor polynomial would be the fourth Taylor term. So what does the fourth term look like? Well, the fourth derivative evaluated at z over 4 factorial, the absolute value of x minus c to the fourth. What we want to do is we want to max this out, this value in the numerator out, and that will be less than or equal to the remainder in absolute value. Okay, so we want to maximize the fourth derivative at z. Now, z is somewhere between 1 and 1.5. Remember, 1 was the center, and 1.5 is the one where we wanted to evaluate. But it tells me the fourth derivative is less than or equal to 3 for all values between 1 and 1.5. So the maximum that this thing will ever be is 3 over 4 factorial x minus c. Well, that's 1.5. That's what I want to evaluate at. X minus c is 1 to the fourth. So that's 3 over 4 times 3 times 2. The 3's drop out. 1.5 to the fourth is 1 over 16, right? So that's 16 times 8. 4 to carry. 1 over 128. Okay, and 1 over 128 is in fact less than or equal to 0.008. All right, so look, what I want you to understand is this. The answer we got here is 1 over 128. This is the maximum error that you can have between this value and the true value if I were to plug f 1.5 into f, whatever it is. All right, so the true value here is negative 1/4 plus or minus 1 over 128. It's somewhere here. I don't know what it is, but I know it's somewhere between these values. Okay, that's the true value of f of 1.5. That's what this error bound is doing. All right, it's not telling you the actual error. It's just telling you about how far off you are, okay, or what's the maximum off you are, plus or minus. All right, let's try one more. So now let f be a function that has derivatives of all orders for all real numbers x. P sub 4 be the fourth degree Taylor polynomial at x equals 0. That's the center. Show that f of 1.4 minus p of 1.4 sub 4 is less than or equal to 1 over 3,000. Okay, so again, this is the true value. This is the approximate value. I'm showing that the error is off by less than or equal to 1 over 3,000. All right, so to do that, I just use the fourth degree Taylor polynomial, or Maclaurin polynomial, its center is 0, all right, to approximate f of 1/4. So x is 1/4, the center is 0, so I'd have to go to the first unused term. If I use the fourth degree Taylor polynomial to find the approximation, then I have to go to the fifth degree term to make it happen. So I need to find the max of the fifth derivative evaluated at z over 5 factorial x minus c to the fifth. Okay, now how do I find the max of the fifth derivative evaluated at z? Remember, z is between the center and 1/4. All right, so now here's the graph of the absolute value of the fifth derivative at x. So the question is, what value of z do I substitute in here to give me the maximum answer? Well, if I look at the graph, I'm looking for the maximum y that I can get between 0 and 1/4, here and here. Well, the maximum value that I can get is here, right? That's the maximum value between 0 and 1/4, but I don't know what this value is. So I'm going to have to, estimate up to the first value that I actually know the value for. So I know this is somewhere in the 30s, I would guess, somewhere between 20 and 40, but I know that this thing doesn't get above 40. There's no doubt, right? This number is definitely below 40. So I'm going to use 40 for the max over 5 factorial. So that's going to be 1/4 minus 0 to the 5th. And now, if I do that calculation correctly, well, let's see, 40 over 5 factorial, 45 times 4 times 3 times 2, and then 1 over 4 to the 5th. Let's see, that's 20, that, and that. Those three all knock out the 40, right? So this is 1/3 times 1 over 4 to the 5th. And that should be less than or equal to 1 over 3,000. So that is the use of Lagrange's error bound. And that's how Lagrange's error bound works. You're trying to find the maximum value for this numerator here between the center and the value you want to evaluate at. Okay? No matter how you need to find it. On a graph, you can find it algebraically, plug the numbers in, figure out which one's the max. All right? That's how it works. As always, thanks for clicking.